PDMS in the study of dynamic tactile interfaces. My mentors are Dr. Loma Kreshmar and Agatha Cadet, and we work in the laboratory for nanoparticle modification at assembly at State College, New York. So, basically this project is actually part of a larger project by Dr. Kreshmar, my mentor, and one of her workers, which is Agatha Cadet. And the goal of Cadet's project is to develop dynamic tactile interfaces that will enable visually impaired and blind people to access visual information. Now, in English, what that really means is that we're designing this sort of a film that can go on top of a touchscreen panel. So you might be at an ATM machine trying to withdraw some money, but then there might be a blind person or someone who can't see us clearly. And this film will be able to create like bumps on the screen so that blind people or visually impaired people can feel the buttons that you see on the touchscreen, and they will be able to maneuver around, and they will be able to withdraw money and do certain things like that. Now, narrowing down, my goal under Cadet's project is to design and create a device and method that can apply an electrical field to a PDMS compound during the curing stage. I'm going to get more into details with that in just a few minutes. This is some background information. What is polydimethylsiloxane, also known as PDMS? It's a silicon-based organic polymer that's known for its unusual flow properties. Before curing, it acts as a viscous liquid, which is similar to honey. So it moves very slowly, but it's still a liquid form. After curing, it acts as an elastic solid, and it's very similar to like a rubber film or a rubber panel. There are applications of polydimethylsiloxane in places such as contact lenses, medical devices, shampoos, caulking, lubricating oils, heat-resistant towels, and many more. Here are some of the materials that are used for this project. They vary from compound-based, compound turn agent to mixing dishes, rubber gloves, electronic bounces, safety goggles, microscopes, vacuum pump, tubing, an oven, Teflon block, and plates, and just many other things. These are only most of it. There's a couple more, but these are the more important ones. Now, this is just a brief explanation of the ingredients inside the base and curing agent. You don't have to copy this down because it does look pretty complicated, but this is just a reference of what the base and curing agent is made of. Now, the procedure is actually pretty simple. The idea behind it is just to combine the base and the curing agent, but it is quite time-consuming. Basically, we start off by creating a mixture of base and the curing agent. The curing agent should be about 10% of the base's mass. Then what we do is we mix it in a mixing dish for 5 minutes. And then we pour approximately 1 gram into a Teflon mass closing block. And before we do that, we need to clean the block with nitrogen first. Nitrogen is actually a very clean form of air, and that allows us to remove dust particles and small particles that we may not be able to see with our eyes. And then what we do is we place it in a desiccator container setup under a vacuum to remove air bubbles. So the bubbles will come out of the compound and just be sucked out of the system. And the entire vacuum takes about 30 minutes, but after the first 5 minutes, we want to remove it from the vacuum to prevent the bubble buildup, and then return it to the vacuum for the remaining 25 minutes. After this is done, we will place it in a 70-degree Celsius oven for overnight. There are some safety concerns with PDMS. It looks like it's, the material looks like it's glue, but it's actually a very unique compound. And you would always want to wear gloves because PDMS on fingers can create great discomfort. They can get into the gap between your fingerprints, and it's very difficult to wash off. So we always have to make sure we're wearing gloves when we're handling this material. And we also have to wear goggles too. I don't know how you can get PDMS into your eyes specifically, unless you're very good at accidents. But PDMS in your eyes is not very pleasant either, so you want to make sure you wear goggles too. Now, the purpose of the electrical field setup is that we want to create a method that can align particles. In this image, you'll see a basic zoomed-in version under a microscope of PDMS particles. And what it looks like is it's pretty much random inconsistencies in material and formation, and it's usually found in clusters, and also it's also very scattered. You can see in the picture. You might have a cluster here and nothing here, so it's very inconsistent, and we don't want that in our material. However, in this picture you'll see a model made from ping pong balls, and we would like to achieve something similar to this. And we can do that by adding electrical charge to the PDMS compound during the curing stage, so that while it forms the polar ends, it will align itself up and create a uniform pattern that's just similar to this model right here. We had some initial design ideas to create an electrical field, and what we wanted to do at first was to use aluminum foil as electrical plates between which an electrical field would be generated. So we cut sheets of aluminum, and we wanted to put them together close enough to generate an electrical field, but not too close that it would create a shortage. But that's very difficult because it's hard to maintain a distance between two sheets of aluminum foil, especially if it tends to bend or fold. Now, we conducted 5 tests in total. And these on the chart right here, that's the amount of base and curing agent we used for each test. For each test, it was unique. We tested a new method or a new component that we decided to incorporate into our design. Test 1 and Test 2 are actually very similar. It was just a basic understanding of how to create PDMS. Test 1 was just creating it under supervision with my co-mentor. And Test 2 was creating it without supervision, just by myself. Test 3 involved unsecured electrical plates. That's what we call aluminum foil without securing it down to the panel, to the block. Test 4 was the same thing as Test 3, except we were able to secure it down so it's airtight. And Test 5, my mentor took the method that we came up with and applied it with the top plate, the second electrical plate. Now, Test 1 and Test 2. Test 1 was created under supervision, Test 2 was created without supervision. So, in this picture, you'll see what it looks like after it has cured. This is a Teflon block, and it has the molding inside here, and that's where we would pour the PDMS compound before we cure it. And we put the entire thing inside the oven overnight. Now, there's a few things about this compound that makes it difficult to work with, and that is once you pour something in here and it cures, it's actually very difficult to remove, and it takes a great deal of force and effort to remove it and pull it out so you get something like this. Another factor that we also noticed is that having a Teflon block like this would also give us a certain thickness of the film that's similar to here. And we want to make this film as thin as possible so we can place them on touchscreens and use it for other applications. So under Test 3, where we use unsecured electrical plates, that's just a fancy form of saying that we put a piece of aluminum foil to act as an electrical plate. And what we did was we trimmed it down to the approximate size and we placed it inside the molding, and we ran it over the side to attach it to the wire. And this wire would allow us to apply an electrical charge. However, there are some problems with an unsecured electrical plate, and that is that with the PDMS compound, it's very liquid-like, and it will seep into any cracks it finds. So what happens with an unsecured electrical plate is that the compound will seep under the aluminum foil and cause a force that would lift the aluminum foil. And when it cures, the aluminum foil becomes trapped in the middle. And that's not good. So, Test 4. We took the same concept from Test 3, and what we did was we wanted to prevent the PDMS from seeping under the aluminum foil.